looks like we're talking about practice 13.1.2. We're still looking at two sample t-tests or z-tests, depending upon whether we don't know or know the population standard deviation. Here's the context of this problem. In a study of heart surgery, one issue was the effect of a drug called beta blockers. It's looking at the pulse rate of patients during surgery. So available subjects were divided at random, that's important, into two groups of 30 patients each. That's also important. One group of patients received beta blockers, the other group received a placebo. The pulse rate of each patient at a critical point during an operation was recorded. The treatment group had, well, and let's write this down. So, treatment group had an average of 65.2 beats per minute with a standard deviation of 7.8 beats per minute. The control group, that is the group that took the placebo, we'll call that the control, had a heart rate of 70.3, and which also had a standard deviation. That's a sample standard deviation of 8.3. So it looks like we're dealing with a sample standard deviation. They didn't give us the population standard deviation, so this is going to be a t-test. Two sample t-tests. Okay. All right. It says perform an appropriate significant test to see if beta blockers reduces the pulse rate. So is this 65.2 merely coincidence that it's lower than the control of 70, or is that difference large enough to cause us to question their equality? That indeed treatment group, the beta blockers, does cause a lower pulse rate. We're going to do this in 4 steps. Step 1, starting now. It looks like we need to figure out the population. And the population here would be all, this is heart surgery. Heart surgery patients. Receiving beta blockers, not receiving beta blockers. All heart surgery patients. It makes sense that you'd want a lower heart rate if you were having heart surgery, right? If you just have something going on, you want to reduce the amount of work that your heart's doing. So parameter. We're looking at the true mean difference between the treatment group and the control group. Our null hypothesis. Is the mean of the treatment group, I'm going to use a T here. Last problem I used 1s and 2s. This one I'm going to use T's and C's. Is the mean of the treatment group the same as the mean of the control? That's my null hypothesis. The alternative is that the beta blockers are doing their work and the treatment group is less than the control group. And I want to test this. Does it tell me? It does not. So I want to test this at an alpha of 0.05. If I see results rarer than 5% of the time, that means I'm convinced that the beta blockers are actually reducing heart rate. There's step 1. It's our conditions step. We are going to identify the conditions for both the treatment group and the control group and identify that they've been satisfied separately. So the treatment group was that a simple random sample? Yes, it was. It was stated. Was it a normal distribution? Yes, it was. It was a sample size of 30, which kicks in the central limit theorem. And how about independence? Well, I'd say all heart patients is indeed greater than 10 times 30. There's more than 300 individuals who have had heart surgery. And so then we go to the control group. And this is going to be exactly the same, simple random sample. In the problem it was stated that yes, it was a simple random sample. Is it normal? In the problem it was stated that our sample size was 30, so central limit theorem for the control group also, so we're good to go there. And independence, indeed, all patients greater or equal to 10 times, oh man, ran out of room, 10 times 30. So we're good to go there. Conditions satisfied. Calculations. So calculations, again, is the t-test because we weren't given a population standard deviation. So here we go, t equals the difference between the means of the treatment and the control sample divided by the standard deviation of their differences. That's the standard deviation of the treatment group squared over the sample size of the treatment group plus, always plus, the standard deviation of the control group squared over the sample size of the control group. I'm just going to drop those values in, and then I'm going to go to my calculator in order to run the computations. So, 65.2 minus 70.3 over the square root of 7.8 squared over 30 plus 8.3 squared over 30. Good to go from there. At this point, I'm going to my calculator, and I'm going to drop these values in where it says stats. So I'm going to stat, over to test. I'm doing a 2-sample t-test. That's function number 4. I'm going to stats, selecting that one. I'm going to drop in my 65.2 and 7.8, as well as my sample size of 30 for my first population here. I'm going to drop in my 70.3 and my 8.3 with my sample size of 30. Now, in this practice problem and the last one, the sample sizes have been the same. It's not essential that your sample sizes are the same for a 2-sample test. Good if they are, unnecessary, however. I'm going to go ahead and select the correct mean 1 is less than mean 2. I'm not pooling, never pool. We're calculating, and here's what we get. It looks like we have a t of negative 2.45, which gives us a p-value of 0.0086. That is a really small probability that with a sample size this large, that there is such a stark difference. Let's go ahead and put that into the context and get this problem concluded. So we need 3 things, as always. We need evidence. We need to make a choice, and then we need to put that choice into the context of the problem. So what is our evidence? Well, I erased it, but it was our p-value of 0.0086 was less than our established alpha of 0.05. That makes our choice really easy. 0.008 is way less. So we have no issue saying that we reject the null hypothesis. And what was the null hypothesis? That the treatment group and the control group were the same. So we reject that. That's not the case. So what's the deal here? It seems that we're talking about beta blockers. Beta blockers reduce heart rate. All right, so that in and of itself is pretty compelling, but the problem goes on, as well we should, to ask how much do beta blockers reduce the heart rate? Is it a large amount or is it a little amount? So in order to answer that question, we are going to create a confidence interval. So here we go. Confidence interval. The problem invites us to do a 99% confidence interval. Let's remind ourselves of the formula. Confidence interval is the difference of the means, and in this case we have our treatment group and our control group, plus or minus T star. T star is a reflection of how many degrees of freedom we have and our confidence level, times the standard deviation of the difference. So that's the standard deviation squared of the treatment group over the sample size of the treatment group, plus the standard deviation squared of the control group over the sample size of the control group. We're going to drop these numbers in and go ahead and tackle our problem. In order to help me, I'm going to use my graphing calculator, and I'm going to run a 2-sample T interval. So that is under my stats function. I'm going to go over to the tests menu, and I'm going to scroll down, 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 down until I find a 2-sample T interval. Now the data, or the stats rather, are still there from the hypothesis test that I just did. So this problem should be relatively easy. Let's drop in the numbers so we can show we know what's going on behind the scenes in the calculator. So the mean of the treatment group was 65.2 minus the mean of the control group, which was 70.3. I'm going to use my table C in order to figure out my T star. Both my sample sizes were 30. 30 minus 1 is 29, so I'm going to use 29 degrees of freedom, and I'm going to triangulate that off a 99% confidence level. So here I am, 99%, 29 degrees of freedom, and that looks like 2.756. 2.756 standard deviations up, 2.756 standard deviations down is going to get me my range for my confidence interval. I'm going to drop in some of these values as well. Standard deviation of my treatment was 7.8 squared over my sample size of 30 plus 8.3 squared over my sample size of 30 for the control. I'm rooting it all, and there we go. Now I'm not going to try to put this into my calculator and have it crunch the numbers for me. It's a lot of opportunities for order of operations there. Instead, I'm going to that menu like I mentioned earlier. So that is stats over to tests down to a 2-sample T interval. If I go on down there and select a 99% confidence interval and calculate that, I get a confidence interval between negative 10.6 and 0.44. So what does this mean? Let's put it into context, and I'll actually use words this time rather than just saying it out loud. I'll write it down. So I am 99% confident the true difference is between 10.6 beats per minute less to 0.44 beats per minute more when using beta blockers. All right, so that went over 0. So it could be the fact that beta blockers don't do anything, right? That's in the realm of possibility. However, there's a lot more on the negative side than there is on the positive side. If we were less confident, we might find that that would shrink up our interval a little bit. So there you go. Hope this helped.